In this video, I'm going to work through an example of choosing a sample size to meet a precision target for a particular experiment. And that experiment, we're trying to estimate the mate preference of female jumping spiders, where we are presenting a female spider with two tethered males, one from her own species and one from another species. And we want to estimate the proportion of female spiders that choose males of their own species. So we're going to imagine that females choose males essentially at random, so that population proportion P is 0.5. And what we want to do is figure out how much data would we need to demonstrate that the population proportion P was 0.5. So one idea to do that is to plan a sample size sufficiently large that we can get a narrow confidence interval for the population proportion, so in other words one with high precision. And then if after we've done our experiment we end up with an estimate of P that's close to 0.5 with a relatively narrow, let's say 95% confidence interval, then we would be able to conclude that the true population proportion, the true preference of the female spiders, is close to 0.5. We can't say it's exactly 0.5, but we would be able to conclude that it's close to 0.5. So in other words, the preference that the female spider is showing for its own species is pretty weak. So that's the setup, and so we're going to try and get a feel for what this experiment is doing and see if we can use that to come up with a suitable sample size. So we'll start off with a sample size of 10, just because we've got to start somewhere, and we'll set the population proportion P to 0.5, and then we'll randomly sample 10 females from the population where P is equal to 0.5, and we'll count the number of times that a female chooses a male of her own species. So the ones in this random sample represents the times that the female spider selected a male from her own species, and the zeros represents times where she chose a male from another species. So this is all totally hypothetical right now. None of this is real data. We're just thinking about this experiment and trying to come up with a suitable sample size. So we're making up data under the scenario that there's no preference. P is equal to 0.5. And then we can calculate the we can calculate the sample proportion and use that as an estimate of the population proportion. So in this case, the sample proportion of times that the female chose a male of her own species is 0.3, so 3 times out of 10. We could calculate a 95% confidence interval for that population proportion, and this was something we covered in a previous lesson, in a previous video, and we're using the Agreesti-Cool method here, and it tells us that we're 95% confident that the population proportion is between 0.10 and 0.61. So that's got a pretty wide span. So the span is the difference between the upper limit and the lower limit, and it's 0.5. So this isn't really meeting our stated goal from the beginning, that we want to come up with a narrow confidence interval, one with high precision. But this was just one sample, one random sample. So we really need to repeat this process a bunch of times to get a feel for what could happen on the average. So let's do it 100 times. I'm going to create this vector. It's an empty vector. There's nothing inside it. So this is going to be a placeholder for our results. And then I'm going to run this loop to fill that vector with spans using the steps that I went through just now. So that's all this loop is doing. We're setting it so that this index I goes from 1 up to 100. And each time through the loop, we're going to generate a sample, we're going to calculate the confidence interval, and then we're going to calculate the span of the confidence interval. And by having the index I in here, in this piece of the code, that's going to fill the ith element of the vector span with the span for that particular sample. So once we've got that, we get a whole series of numbers representing the span of the confidence interval, and then we could graph that in a histogram. So there's a histogram of the spans, and we can see here that having a sample size of just 10 probably isn't going to do it, because the best we do is a span of a little under 0.48. The worst we do is a span of 0.53. We're not getting what we want here. We're not getting a narrow confidence interval. So we need to increase the sample size. So let's just go in stages. Let's double it first, and repeat that whole process, and then draw the histogram again. And so we're doing better. Okay, we're getting a narrower confidence interval if we use a sample size of 20, which is as should be expected. But it's still probably not good enough. It's ranging from, what is that, 0.35-ish up to a little bit over 0.4. We'd really like to get it down to be a little narrower. So let's set a target of having a span no greater than 0.2. So in other words, we want the right-hand edge of this histogram to be at 0.2. How much do we have to increase the sample size by? So let's double it again to 40 and see what happens. Okay, so we're getting closer. We're going between 0.28 and 0.3 roughly, 0.295. So we're still not quite where we want to be. Let's double it again. What are we up to now? 80, I think. Okay, so now we're in the ballpark. We're getting down to spans of around a little bit over 0.2. If you play around with this yourself, I think you have to go as far as a sample size of 93 to actually get a histogram that's bounded above by 0.2. So all of the spans from these 100 samples where we had a sample size of 93 have a span of no greater than 0.2. So if we were going to run this experiment with the spiders and we wanted to meet that goal of obtaining a confidence interval, a 95% confidence interval that has a span no bigger than 0.2, then we would need to have a sample size of at least 93 to meet that goal. So that's an illustration of planning an experiment and thinking about the sample size that we're going to need to meet a particular precision target. And in the next video, we'll consider trying to meet a power target instead.